Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. This is me, Tanvir Khan, student of Mechanical Engineering Department studying Manufacturing and Automation Systems. So today we will model a regression artificial neural network model for the given data set. The data set is about the Tesla stock data. So you can see here, this is the given data set which comprises of date, the date of the recorded stock prices, often prices, uh, the price of the stock at the market open, and high represent the highest price of the stock during the day, low represent the lowest price of the stock during the day, close represent the closing price of the stock, and adjust close represent adjusted closing price which takes dividend and uh, which take dividend stock splits and new stock offering into account. And the final one is volume, so the number of share traded during the day. So these are all like the data features that we have uh, in our data, but we will exclude this date column from the given data, and we will take the close as a target variable, and open, high, low, and volume we will take these uh, four column as a independent variable input factors. So I already excluded this one and arranged all the things accordingly. You can see here. So open, high, low, and adjusting close price and volume. I I'm going to take these columns as a inputs variable and close price as a target variables. So this is the data about the Tesla stock data from um, 2010 till 2020. So we will analyze this data to predict the closing price. So we will construct a artificial neural network regression model for this given data. So we will open the Matlab. So before going to develop a model, we need to know about our artificial neural network. So, so artificial neural network consists of inputs, neurons, and outputs. So neuron is responsible as like in our brain, like that is mimic like our brains neurons like that are transferring signal from one location to other location. So neuron is like acting like the same way as our brain. So the basic the most simple architecture of the artificial neural network is this one, which represent the single input to the neuron. Like you can see here, there is a single new input p to the neuron, and a is the output of the neuron. So this represents the single input neuron architecture, and there are like multi-input neuron. You can see here like there are multiple inputs to the neuron, and then we get the activation of output, like you can see here, and in which the W represent the weights, B represent the bias. By sometimes scientists, sometimes some expert also call bias, the name is like offset. So we can also use the name offset as well. So this is analogous to the this activation function is analogous, like the output from this neuron before feeding to the transfer function or activation functions, that is analogous to the line slope line slope equations like y is equal to mx plus c, in which m like there is slope, there is here is bed, you can see here, and there is like b represent, so here b represent the intercept. So the b represent biases, w represent the weights, and so when we get the uh, when we combining the weights with the input and adding with the biases, so then after that we feed the output, this one output to the intuition function, so we will get the activation output. So this one is the simple one, and this one represent the multiple, like we have multiple inputs, and there are like as we can discuss, like there might be one input or more than one put, so there is also possibility of more than one neuron, so we can have multiple neurons, and the same way as like multiple layer as well. So you can say here like there are multiple layers of neurons. So this represent the first layer, this represent the second layer, this represent the third layer. But uh, we also called, like some expert also called this input layer as a zeroth layer, this represent one layer, this is a second layer, third layer, and so on. So we, but in this book we like don't use like input layer as a zero layer, so we only call it input layer. And this is the activations, like output of the whole the um, configurations and artificial neural model. This is the output of the all this one model. We also have some transfer functions, like here we can see here we get, like we combine weight with the input, and then we add up the biases, then we feed those that out output to the like output, that output act as an input for the transfer or activation function. So we have a number of activation functions depend upon the like when we need that, so we can use either of them. Like we have a number of transfer functions here. The first one is hard limit. When n, like as I showed you, like n represent this one w p is represent input plus b, so n represent this one, this one wp plus b. So f is less than 0, so we can represent as a equations output as a is equal to 0. So you can see here f is n is equal to 0 or greater equal to or equal or greater than 0, we can um, our output will be is equal to 1. The same way, like symmetrical, hard limit, linear, we can also represent as a Matlab function as hard limbs and pure limbs, and saturated linear, like these are the conditions. So if we get the n value less than 0, so we can apply this one, and in the same way, like if n is equal to, if n is greater than 1, so uh, we represent a is equal to 1, like activation. So we can use all these functions according to our needs in our artificial neural network model. These are the log sigmoid. So these are the parabolic tangent sigmoid, and positive linear and competitive. Like we can use either of them according to our needs. So let's start from the script. So we will first start from the script. So here uh, so first we will reading the data from the Excel sheet. So the Excel sheet is here, which name is like my name is Tanvir Khan, so I named that Excel sheet as Tanvir Khan. You can see here, and we will access this sheet number. I named the process data, so I will access uh, this one data into MATLAB script. So let's start. So first we will starting the importing data, importing importing data. So we will name the input as input is equal to, we're going to read Excel, so Excel sheet, so XLS READ, and then name the Excel sheet file number name, and uh, this is the file name, and this is the extension XL S SX. Okay, so this is extension, and this represent the sheet number. I name is processing processing data. Okay, processing data, and then I will access the range of the data, like here you can see I will access from here till the last, from here. So this is the E, this represent E, and this the first one and this was the this one is the column number. So this one is the row number, and this was in the column number, column representations, like the E, and this so E N A3 N E. So we will access in the Matlab. This represent the A3 into E2, uh, as our range is A2 to A2 to 1 A2 to, you can see here 2418. So we will 2418. Okay, and then okay, 28, sorry, now it's good. uh, Close the bracket, and so this will read the Excel. So we mean when we run this one, so it turn on Excel, where GWR KHN XL XLS, yeah, it's XLS read. mm, Met. We also have this one here, so I will copy from this one. um, I'll copy from this one and paste directly. So now we will run this one. So it is run automatically. You can see this one is the data I imported from the Excel sheet. Then I will then I will import the this one target. So I copy this one, and this I already performed this one time, so like it will take time if I write down all the code, so it will take time. This way I'm just copying from there. So this will be the target variable, like you can see here. The target is target is there. So this one represent the target. So we will import target start from a f3 until uh, f3 until 2418. Both are the same number of rows, so that's why the rows number is same, only the column is different. So f3 is imported, so I will also import this one and just run. Okay, so already been imported the target variable. Then we will start from the, we will take the transpose. So I will copy this chunk of code, paste here. So we'll get the transport first. I will get this transport. So it convert from rows into columns. So you can see here already being converted from this one to this one. So five represent the, as you can see here, this one is like rows represent features and column represent samples. You can see here the same way is like we transpose the target as well. Okay, so target is also been transposed. Now we will take uh, this one, copy in one by one like this one. Okay, copy this one. So it's the actually the configuration of our artificial neural network. This represent the how would be like artificial network model, like it represent neurons. So number of neurons, but here the I will take the layer number as one, so don't need, because later on we will add number layers number, so we'll increase the layer numbers, so then we see the result as well. But for now on, we will only analyze for neuron and for the training algorithm. Like here we can also give this name coffee, like represent the train algo. I have given the name train algorithm. Train algo. Train algorithm is equal to, so from here I will just copy this one and yes, feed is a argument to the feed forward network. So like here is like we will start simple model, like we will only feed the neuron up to uh, 5, and we will use training algorithm as a train beer. So train beer is basically the algorithm that used for, we also call based on regularization, which is a type of supervised learning algorithm used in training of artificial neural networks. It is especially used for the avoiding overfitting and improving generalization of the network by using regularization techniques. Okay, so like before, so this is the last lecture we attended. We do generalization. Sometimes we need a model in generalized form, like we can use in other situation as well. So for that we do our model should be generalized form, like we can use in any situations. So and also the model should be in simplified form, like not too much complicated, like they have simple they have low number of neurons and they have low number of layers, something like that, right? And we started like there are some ways of generalizing to make the model in generalizations. So there are various ways like growing and pruning, right? So The growing is like we start from the simplest model and then we grow up, we add neurons and layers and so on. And pruning is like we start from the large network, and then we just like remove neurons step by step so that the performance degrades significantly. And global search, we can also select the best one architecture for the configuration for the artificial neural network by genetic algorithm that give us a set of optimal architectures configuration for the uh, artificial neural network. So we can choose one of them and then we apply for use for our problems. So regularizations. So we are choosing the chain Bayesian's regularization. So that is basically we are constraining the magnitude of it, not the number of uh, network weights. So this we are doing generalization just to remove the overfitting problem. Like you can see here, this is the original function. This represent the train network response, and this one the noisy data points. Up to this point, it represent overfitting, and it cannot predict the when we like use for like if we train the model and if we use for the um, uh, new new input variable, so that can predict very well. So that's why it do poor extrapolations. So we can avoid overfitting and what like these are some kind of good interpretations, like it represents the overfitting up to here, and this area represent is the four extrapolations, and the same way as like this one. Okay, we should choose the optimized algorithm to avoid these kind of problems that we are going to face. So for that, we are choosing the Bayesian regularization. So the Bayesian regularization is like this one, in which this represent the sum of error term, and this is the sum of square error term, and the sum square weight terms. And these alpha and beta represent the regularizations parameters. You can see here, yeah, the sum of square error, as I said, like ed represents sum of square error, and sum of square aw represent sum of square of the weights. And these terms like alpha over beta, that control the complexity of the neural network. So apart like if the ratio is here, if the ratio is like 0.01, so the that one is will be the best model. If the ratio is like below than this one, that will be like a poor model. If is the ratio is greater than 0.01, it will be like the curve will be more like smoother and smoother when you increase the uh, this alpha over beta ratios. And this represents the Bayesian regulation to adjust the parameter automatically. These things are will be done automatically by the the train BR function in Matlab. So we don't need to like give these formulas to the Matlab. It will do automatically from for us. So D represent here in this formula, D represent the data set, and choice X represent input and input vector, and M represent choice of artificial neural network model. Okay, so this is all about the regularization, why we do a regularization to make our model more accurate, to avoid overfitting. Yeah, so let's start onward. Okay, so that's why I choose the train viewer first, and then I will also use the another algorithm, optimization algorithm, that is called like Leverberg. So I will choose that one. The second one first, I will try this one. Okay, after this one, we will test the model and write the prediction result to the Excel sheet. Copy. We'll write the okay paste. So this will predict the uh, predicted target, and then I'm going to save this predictions results to the same Excel sheet to the G3 cell. Okay, and then after I will calculate the mean square root mean square error. So I will copy from here, um, paste. So this block of code will calculate the root mean square error, like we also know like the formula is this one error prediction minus target. First we will target error, then we will square root the mean of the errors, this one. So this will give us the root mean square error for all the data. Then I will save the this root mean square error in the Excel sheet on G1 G219 cell, and then I will draw the target with prediction plot. So I will plot the so I will plot the target with predictions, and then I will you can also extract the biases and the um, biases and weights. So we can also extract from the model weights and biases. This represent the weights from input to hidden layer, and this represent the bias for the hidden layer, and this one represent for the weights from hidden to output layer, because it to represent output layer, one represent hidden first, like one layer, first layer, and then output biases represent by we can extract from the network through this line of code biases for the output layer. So this is for this simplest model, and then we will use later this one like what kind of function. So so we will going to run like there is nothing now. So we will name is predicted close price. Okay, sorry, not from there, cut. Okay, so we will close this one to save, like we will going to run. Okay, so we are going to run. Okay, so you can see here this is the result of the graph of target with predicted closing price. So it is perfectly co-line with the actual one, target one. So our model is good, and you can see here there are 5 inputs and 5 neurons. You can see here this is represent 5 neurons, and this is our outputs, like we have one output, so only one output represent this one. Okay, now again we will go there, open this Excel sheet, and then you can see here this is the predicted results for the given data sets, and this one is the represent the error, like this error, like root means square error, root means square error. So this will represent 0.00787 because our data are too much, so that's why like we don't have much error in our data. As we have more data, so our accuracy will increase. Now, like according to this one, the first we also describe the problems, like we have Tesla data stock, uh, and Tesla stock data. So we are this is the present of the Tesla stock data, and uh, artificial. Then we develop artificial neural network. We also importing the data like input and target data. Then we configure the artificial neural network. Then we train the model like we then we train the model like here. Uh, this one, and then we test the model from here. So we did all these things. So we are done with the one, and we are also done with the second one. Now we will changes the algorithm as well. Like I choose the Bayesian regularization algorithm. So then optimization algorithm, I will choose the now Leeuwenberg-Marquardt algorithm. So I will choose that one now, and so we will see the result, like what how it affect the results. One by one we will change the for the same I will choose the other algorithm. So let's start. Replace refresh this one, the um, LLM. So this algorithm, Leeuwenberg Marquardt, so which is a highly efficient and widely used method for training artificial neural network. It is considered one of the fastest training algorithm for the moderate size network, and is particularly well suited for the function that we like going function like regressions and pattern recognitions. So this is the fastest algorithm you can use in this one. Okay, so now now we will see the result of this one, but for that I need to save the result. This one is G3, so I will GH. Okay, I will change by GH3. So our result will be saved here. The same way I will change this one as well to into H, so we can get the root mean square error. So this is the H3. So okay, so there we will change H3. Okay, so it already been changed, and now it will be uh, um, 2 4. It will be H now. Okay, so let's see what happens. We will again run this program. Okay, save this one and close, and again run. Sorry, this one, run the program. Let's see. Okay, we got our results. Okay, so you can see here we are using Leeuwenberg Marquardt. So all the same configuration, only change the algorithm, optimization algorithm. Now we will see the result again. What is the difference? Yeah, this is, we already discussed, this is the fastest one. So this is only for the simple model, not for the complex model. But the accuracy between the error is much higher than the previous one. So Bayesian algorithm is much better than the Leeuwenberg. So we can go for the Leuven Bayesian algorithm. Okay, close, and this one we will again change. So this is for the we will Bayesians. Okay, train VR. We will train VR. Train VR algorithm, and this one is train L and Liebenberg algorithms. We will start again. Uh, we will start again by train by decreasing. Now we will change the uh, neuron. Okay, so if we change neuron, or if we choose like neuron or neuron, like I choose here how much neuron, five neurons, so I will choose the 10 neurons. Then we will go for um, 10 15 neurons. Okay, we will check for this one by using this one training algorithm. Okay, so not this one. Okay, BR Bayesian algorithm. So we will check. This one was for the five. Sorry, this one for the five, and this one for the 10 and 15. We will change one thing. Like first I want to change the neuron number of neuron, then we will change the layer as well. Then after that I will change the transfer functions. So we will start from here now for 10 neurons. So let's go there. This, what was there? Look, um, wait. Mm, let's represent ij. Okay, so I go to the script, and I will go for the 10 neurons. Okay, and then I'll change this by I. Okay, and this by also by I, so we can get the results. So now we should run for the 10 neurons. So what's the difference? Okay, okay, so sorry, um this one, and now we will see the results. So yeah, the error is much higher than the previous one, but I didn't change. I think I didn't change my wait. I didn't change the um, training. Yeah, that's why shows too much error. We will change this algorithm to Bisons, and again we will delete this one for now on and delete. Okay, and save this one again, and we will run the code again. That's why it shows the too much error. Let's wait because I have too much data. That's why they are taking too much time. Okay, you can see it now change based on regularizations. So now we will check the results again. Check this. Yeah, now you can see that the error is much smaller. So but as compared to this one, now we increase the neuron, but the error is smaller than this one if we have five neurons. So by increasing neuron we get a good result. Now we will try for the j 15 neurons. Okay, now we will try for the 15 neurons. First I will save this one and okay, now we'll try for the 15 neuron. So let's see what happened. Okay, now we'll run. Now we'll okay. We will also change this one J and this one also to save our data and the specific locations. Okay, now see what happened. Okay, so we got our results for the Bayesian algorithm. Now we'll go to the file and check the what's the error. So now you can see here error a little bit increases. So we discussed already if we increase the number of neuron more than the optimal level, so our model accuracy will be also degrading. So and hence it proved like first we increase up to 10 neuron, now we increase up to 15 neurons, so the accuracy goes down. So it means like neurons like play an important role in accuracy. So it doesn't mean like if we increase the new number of neuron, so our model will be give us more accurate results. So it's not like that way. So we should keep our model simple so to get a good accuracy. Okay, now we will change the this is for the 15 neuron, this is for the 10 neuron, and this is for the neuron 5. Okay, I will name it neuron 5, neuron 5. Okay, so this is for the neuron 5, number of neuron 5, neurons 5. Okay, so now I will check by hidden layer. Okay, hidden layer, I will add one hidden layer 1 and then 2. I will check by 2. Okay, hidden 2, layer, layer 2, layer 1. Okay, so sorry, 2, and this is 2, this is 3. Okay, I will check by adding the layer inside there. So I will use now for this one K. So K and L. Okay, number of neurons here. I will add the vectors for vector 15. Okay, let's see what happens now. And we choose K3. Okay, K3 here, and we will see K3 prediction here and the root mean square error here. Okay, now we'll save. We'll save this one as well and close this one, and then we will run this one. Let's see what happens if we increase the number of iterations. Okay, number of layers, sorry, taking too much time because my data is too much, so that's why taking too much time. Let's see what happens by increasing the okay, taking too much time because we have large data set. Okay, it's okay. Now we will see. Now we will see the result. What happens? Yeah, the error increases if we add another layer. So now we will try adding another layer, so as compared to this one. Okay, this is for the 10 neuron, this is for the 15 neuron, this is for the 5 neuron. This is for the layer 1. If we add the layer 1, um, you can see here. Now we will try the layer 2. Okay, layer 2 for the given data sets. What then we will see how it affects the model. So we will add L. Okay, new model L. So I will change this to L first. L and L, and here I will add another layer in. Okay, I will keep the number of neuron in each layer the same, 15 15 15. Okay, so I'm not going to change that one. So let's start. Let's first save this one and cancel. Now we will see here. It's taking too much time because we have large data sets. Let's wait. Bayesian regularization algorithm is good for modeling the neural network. This is the best optimization algorithm because it gives us less error as compared to the Leeuwenberg-Margot algorithm. Okay, let's see what happens. Okay, now we will check the result. Check the result. So it was too much, complicated model, so that's why it took a lot of time. Yeah, now the accuracy improved uh, by adding another layer. You can see here uh, in the number of neuron. So you see the effect of adding layer. Now we will see the changing the transfer function. Transfer functions. We will try two transform functions. Transfer functions. FC1 and FC2. Okay, we will try these two, and let's save the result first here. Let's save the result first here, and we will make our model simple so it takes less time. We will reduce to 5 again. um, oh, one thing here, like we can also extracting the biases, like here you can see here biases and weight. Like this is for the this one, like this is for the output layer, so we can use the another one for them. So this one will be the for 2 to 3 layer. Okay, this is for the first layer, this is second and third layer. Okay, so this will be 3, but this one will be for the middle. Remove this one. So 2 3 3. Okay, this is 2, this is 2 second layer, this is 1 first layer. Okay, so we can, and this way we can extract the biases and weight. Like you can see this is for the first from the input to the hidden layer. So, and this one from the first layer to the second, and this one from the second to the third. So and so on, we can extract the biases and weights in a similar way. Okay, for now we don't need the biases and weights, so we are only changing the transfer functions. So we will change neuron now, neuron now 5. Okay, and we will we will use the train uh, the model by algorithm, by Bayesian algorithm, and also we will use the log sigmoid functions. Okay, so we can use the this one for the first one. Okay, like we assign the we assign the layer 1 transfer functions, say log sigmoid. Okay, then we use the equivalent as well, but from now on we are using only the log sigmoid functions. Okay, and we can also check the transfer, this one, sorry, uh, can also that will be display coffee, and here we can, it can also display as the algorithm as well. Okay, um, and so layer 1. Okay, it's okay. Now we will go to the, and then SM, right? So now going, if we choose the transfer function log sigmoid, so what will happen? Okay, then we will change the prevalent, no, sorry, no, we will take the this one, not the sigmoid function. I will do 10 sig. Okay, we will take this 10 sig, tn sig, not the 10 sig, 10 sig, sig. Okay, we will take this one, tansig. Okay, we'll take these functions, and then try then we will try the other functions as well, like this one, maybe the log sig as well, log sigma prevalent as well. But for now on, we're going to change only this one function. So let's see what happens. But we also change the where to save the data m in m column. So we will change this one m, and we also change this one into 4194. Okay, let's see. For now on, we will this one off. We don't need this one. So this is just only for the biases and weight extractions. Okay, so let's see what happens. We will save this first and M. Okay, let's see what happens. M, we are going to work on M, so that's why let's go intrinsic. Okay, no, it's going past because we have choose model simple. Okay, now you can see our transfer function is transig 10 sig. Okay, so we will see the result now. Now the accuracy is a little bit dropped it, but we will compare with this one because I choose the 5 neuron here and 5 neuron here, so as compared to this one it is better. The result is better. So transfer function also affecting the accuracy as well. Okay, now we will save this one and we will change the transfer functions and n column. Okay, and first need to change n mm, n n to n. Okay, so we are going to assign the functions log sigmoid, log sig. Okay, we'll call sig. Let's see what happens. Log log sig. Okay, log sig. Yeah, logc. Now the n3 and n2 everything is perfect. Okay, now we will run the n3. Okay, and yeah, now we will run the code again and let's see what happens. It increase the error or whether it is decreasing the error. Yeah, now we will see here. Hmm, it is a yeah, it decreases too much. So log sigmoid is much better than thin sigmoid, right? So log sigmoid is much better than the power 10 sigmoid. This one functions. Okay, log sigmoid is much better than the 10 sigmoid function. So we cover up all these things like first we check with the number of neurons. So first we increase the number of neurons. The uh, the error increases like you can see here. You can see here like 5, the first three. Wait, this is for that. I will three, 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 three. We'll go with the or with the other color, maybe this color. Okay, so this is for the neuron and this one as well, 515. Sorry, so this one is also, but okay. So this is for the neuron, and this one was for these result for the hidden layer, and the final one is for the transfer functions. So here you can see this one is this one. This is for the uh, Levenberg function algorithm. And this is for the Bayesian algorithm for the same number of neuron, but we then so we comes to the conclusion like Bayesian is much better than the Levenberg, and then we add up neurons like 10 neurons and 15 neurons, so the error increases. So while increasing number of neurons, so the error increases. And while changing the hidden layer, increasing the hidden layer, so first it increases the error, then decreases the error, right? And for the transfer function, so log sigmoid, and this is for the tens uh, tens seg, okay. This for the tangent sigmoid functions, tens seg functions, transform functions, and the other one is for the sigmoid, log sigmoid. So log sigmoid function is better than the tangent sigmoid function here in my case. So it give us less error as compared to tangent sigmoid functions. So the overall conclusion is like if we increase the number of neurons, so the accuracy will be affected. If we increases the number of less, so the accuracy will be affected. If we change the transfer function, so the accuracy will be also affected. So we cover up the three number three, like topology, artificial network modifications. We change the algorithm, then we change the number of neurons, then we change the hidden layer, then we change the transfer functions. So we discussed like what how it affected the result, like the model accuracy. So we already discussed. Now for the fourth one, now I will try in the next video the graphical user interface to do the same task. Okay, uh, so goodbye. So this one is the overall code for the simple one. Like this is my name, and this is all for the script code for the artificial neural network. This I put here the code, one line code to display me the transform function we are going to use. So it shows me logsig, right? Last time I used the logsig, it shows me logsig mode functions. Okay, so goodbye. Assalamu alaikum warahmatullahi wabarakatuh.